calculating Cohen's d from SPSS output. Unfortunately, SPSS does not report Cohen's d if we apply a t-test. So we have to calculate Cohen's d by hand. This is relatively simple. Let's have a look at some t-tests. First of all, a one-sample t-test. In this example, I test the null hypothesis that population candy weight is on average 2.8 grams. In our sample, we find a mean of 2.836 grams. So our unstandardized effect size is what we find in our sample, 2.836, minus what we hypothesize in the population, 2.8, or a difference of 36 microgram. This is our unstandardized effect size. If we want to standardize it, we have to divide by the standard deviation. The standard deviation is reported in the one sample statistics table. It is 0.169. So we divide by 0.169 to obtain Cohen's d of 0.21. This is close to 0.20, which, according to our rule of thumb, is a weak effect size. Our second test is a paired samples t-test. I compare candy colorfulness after exposure to sunlight to colorfulness before exposure. Colorfulness has clearly gone down in our sample from 7.3 to about 5.4. So there is a difference of about 1.9, and this difference is reported in the column mean in the paired samples test table. In this example, the difference is negative, but you should ignore the minus signs. So we have a difference in our sample of 1.880 rounded to 3 decimal places. This is what we find in our sample. The implicit null hypothesis is that there is no difference in the population, 0. So we may subtract 0. But of course nothing changes. Our unstandardized effect size is 1.88. To standardize it, we have to divide by the standard deviation. This is the standard deviation of the difference, and it is reported in the paired samples test table as 1.033. So I divide by 1.033 to obtain a Cohen's d of 1.8. Now, can that be right? A Cohen's d above 1? Yes, it can. Cohen's d can be larger than 1, and it just means that we have a strong effect because it's well above 0.8. Our third and last t-test is an independent samples t-test. Now I'm going to test the null hypothesis that in the population, red candies and yellow candies have the same average weight. In our sample, there is a slight difference. Red candies on average weigh 2.8 grams, whereas yellow candies weigh about 2.75 grams. The difference in our sample is reported in the independent samples test table under mean difference, where we see an unstandardized effect size of 0.05. Remember, the implicit null hypothesis is that there is no difference, 0 difference in the population. So what we find in our sample is actually the difference between what we find and what we expect. To standardize the effect size, again, we have to divide by the standard deviation. But it's a special kind of standard deviation, a kind of average of the standard deviation of weight among red candies and among yellow candies. So it's somewhere between 0.15 and 0.19. Now this combined standard deviation, which is called a pooled standard deviation, requires some squaring and taking a square root. Instead, we use a different approach. We take 2 times the t-value and divide it by the square root of the degrees of freedom. Now in this example, the f-test on equality of variances is not significant. So we may assume that the variances are equal in the population. So I will take the information from the top row of the independent samples test table. 2 times the t-value, which is 0.651, and we have to divide by the square root of the degrees of freedom. There are 18 degrees of freedom, the square root is about 4.2, and the result is 0.31. So in this example, Cohen's d is 0.31, which is closer to 0.2 than it is to 0.5, so we would say that the effect is small. This concludes the presentation of how we calculate Cohen's d from SPSS output.